Dear students, good morning. Today we'll continue the valence bond theory with respect to some more examples which are mentioned for your studies. Okay. So now yesterday you have learned the main postulates of valence bond theory, and also we have discussed the valence bond theory with respect to one example, that is FeCN6 4 minus. Okay. Today we'll take the next example, that is FeCN6 3 minus. So similar to the previous one, given here also the central metal atom is Fe, and ion is Fe plus 3. That means in the complex the iron exists in the form of Fe3 plus ion. Okay, the atomic number of Fe is 26 and its electronic configuration is argon core 3d6 4s2 4p0. But during the formation of this complex, metal ion attains stable oxidation state by losing 3 electrons. So the 3 electrons means 2 electrons from 4s, these two, and 1 electron from 3d. So thereby totally 3 electrons are lost to attain the stable oxidation state, that is plus 3. So its outer electronic configuration is 3d5 4s0 4p0 after losing 3 electrons. So here it is 3d5. So now orbital picture, the 5 electrons are distributed singly in 5d orbitals. So 4s is 0, 4p is 0. Okay. So now here the cyanide, reacting cyanide, is say monodentate in nature and it's a strong field ligand and it is negative ligand. Okay. So now when the ligand field created by the 6 ligand, that is 6 cyanide ions, approaches the central metal ion, then as you know it is a strong field ligand, it forces these electrons. So when they interact with the electrons of cyanide interacts with the electrons of metal ion, say the due to the field strength, that means strong field strength, it forces these electrons to pair up, which is against Hund's rule. So now 5d electrons are forced to pair up in this way. So they are placed in 3 orbitals of 5d. That means out of 5 d orbitals, 3 orbitals are now occupying 5 electrons. 2 plus 2 and 1 electron. So by making 3d orbitals empty. So now the metal ion, according to first postulates, it keeps ready 5 atomic or 6 atomic orbitals to accommodate the electrons which are donated by the ligand. So the 6 atomic orbitals are 2 of 3d, these two, and 1 4s and 3 4p. Totally 6 atomic orbitals, 3d, 1 2, 4s and 3p. So now these, according to second postulate, the empty atomic orbitals undergo hybridization, and here the type of hybridization is said to be D2sp3 hybridization. Okay, so now say the type of hybridization, okay, is D2sp3. Once again 6 hybrid orbitals are obtained. So now the metal ion interacts or reacts with the ligand, means during the bond formation between the metal and ligand, the empty hybrid orbitals overlaps with the filled sigma orbital of cyanide ion. Okay, so now thereby the electrons which are donated by the ligand are placed in these orbitals. Now D2sp3, they are 6 in numbers, and these orbitals are now no more atomic orbitals, they are said to be hybrid orbitals, and thereby the electronic configuration of Fe3 plus in the complex is 3d5. Okay, now the 2d electrons are involved in hybridization, therefore it is a bunch of 6 orbitals. It is a bunch of 6 orbitals. 6 orbital, and therefore the configuration is 3d5 d2sp3 raised to 12, because there are 6 cyanide ions. Okay, and now this will be the electronic configuration. Okay, now as per the see geometry of the molecule, it is octahedral in structure. Okay, this is the octahedral picture, and one unpaired electron is present in the d orbital, hence it is paramagnetic in nature. Okay, so now ligand field is a strong field, thereby it makes the inner d orbitals empty, hence the complex is said to be inner orbital complex or high spin complex or spin free complex. Okay, this much is the explanation regarding this complex ion. So now we'll move on to the next one. Say example 3, valence bond theory with respect to Fe(F6) raised to 3 minus. See, the coordination number of iron is 6. Okay, and fluoride is the ligand, and it is a weak field ligand. Okay, once again it is a monodentate. So Fe is the central metal atom with electronic configuration ergon core 3d6 4s2 4p0 4d0. Okay, so now when the fourth shell is existing, then all the subatomic orbital are going to exist. Okay, if they are involving in bond formation, only we can show them, otherwise no need to show those orbitals. Okay, so now in this case fluoride is a weak field ligand. Okay, iron is the central metal atom, and once again here iron is in +3 state, thereby so during the formation of a complex the iron attains stable oxidation state by losing 3 electrons. It attains +3 state, and its outer electronic configuration is 3d5 4s0 4p0 4d0. So orbital picture is 5 electrons are distributed like this, and these are the empty orbitals. So the approaching ligands are 6 in numbers, therefore they need 6 m orbitals to accommodate or interact. So thereby the metal ion keeps ready, say 1 4s, 3 4p, and 2 4d orbitals. And here the approaching ligand field is weak, hence it is unable to force these electrons to pair up. So thereby they remain as it is, okay, in the d orbital, and the next 6 atomic orbitals are utilized or they undergo hybridization of type sp3d2. Okay, so now the electronic configuration of Fe3 plus, okay, after the formation of the complex is 3d5 sp3d2 12, because these empty hybrid orbitals overlap with the filled sigma orbital of fluoride ions, and they results in the formation of this complex. Okay, formation of this complex. So now the electronic configuration one can write like this. Okay, so now as per its geometry, okay, it is octahedral in nature because the type of hybridization is sp3d2, and it is containing, this complex is containing 5 unpaired electrons in its d orbital, hence it is highly paramagnetic. Okay, so outer d orbitals are used, outer 4d, not the 3d. In previous two cases inner 3d orbitals are used because of the approach of strong field, but here the approaching ligand field is weak field, hence it is unable to force these electrons or to make inner orbital empty. So thus in this case it is said to be outer orbital and highly paramagnetic. Okay, and next it is also said to be high spin complexes. So outer orbital geometry is octahedral and it is highly paramagnetic in nature, and the structure is octahedral, similar to the, see this is the same picture even for the this one. Instead of cyanide, here we have to write down F. Okay, or we can show Fe. So there are 6 fluoride ions. So one is above the plane and the one is below the plane. So these are the, say, 4 fluoride and single the central Fe. They are in the same plane. One is above the plane and the one is below the plane, and the structure is said to be octahedral structure. Okay. So this is the explanation regarding the complex ion, that is Fe F6 3 minus. Okay, we'll continue in the next class. Thank you.